So let us start. So I think so actually many people actually asked to solve some of the problems based on the previous understandings. So in the assignment whatever I have given, right, so I will try to solve some of the problems so that actually we can be completely sure on what we are going to do. Got it? Okay. So note down this problem. So I think so in the assignment question number 13. So weights W1 and W2 weights W1 and W2 are fastened to a light inextensible string ABC at the points B, C, the end A being fixed. Prove that if a horizontal force P is applied at C, and in equilibrium AB and BC are inclined at angles theta phi. To the vertical. Then P equal to W1 plus W2 times of tan theta. And the same is equal to W2 times of tan phi. Now this is the problem statement, right? So first of all, actually when we are solving the statics problems, right, so the fundamental thing is you have to identify the diagram based on the problem statement. This is very crucial. So once you identify the diagram, then actually you can look for the angles that are subjected with different strings or different rods, whatever he has given. So based on that, actually we will be applying the fundamental theorems of maybe Lami's theorem, or maybe actually horizontal component should be equal and vertical component should be equal, so that actually the body is under equilibrium condition, right? So here actually, if you notice, the problem statement is weights W1 and W2 are fastened to a light inextensible string. Inextensible string means you cannot stretch further. So that means that is so stiff enough that actually it cannot elongate. So that is the kind of string. So ABC at the points B, C, the end A being fixed. So that means there is one particular point A where this string got fixed, and then so there are two different weights that are subjected to this particular string, and then these are so B and C. That means like this. So here one weight W1 and here another weight W2 are acting. Now see this, the end A being fixed. Prove that if a horizontal force P is applied at C, so this is point B and this is point C. So at this particular point there is a horizontal force like this. So this force is P. So this is the diagram. So P is applied at C, and in equilibrium condition, so AB and BC are inclined at angles theta comma phi. So this is AB and this is BC. So under equilibrium condition, AB is making an angle of theta with the vertical. So this angle is theta. And BC is also making an angle of phi with the vertical. That means, suppose, so see this. So this is BC, and this BC is making an angle of something with the vertical. So if I draw a line like this, then actually, so this one is phi. Got it? So if I extend this further, so if this angle is theta, this angle is also theta. So these are actually alternate angles. Got it? So this is how the situation is. So AB and BC are making an angle of theta with phi. So this is the horizontal force. So based on this understanding, so we have got actually three different points. So this is one point, this is another point, and this is one point. Now actually he is talking about the weights and the angles, because actually P is equal to W1, W2 tan theta, and the same should be equal to W times of tan phi. So he is talking about these two particular points. So you don't need to worry about this particular point. So here actually this is a string. This string actually is having a tension within it. So that tension actually, I think somebody asked me, so how we can manipulate this tension? So tension means, suppose if I take a thread, so if you tie like this actually I am applying force on either sides. So in that case, what is happening is, there will be a force that is acting towards this direction, and there will be a force that is acting towards this direction also. Now within this particular string, so let me show you once. Yeah, sorry. So if I take this particular string, so this is a string. So this particular string actually, if I drag like this, then actually my left hand actually dragging this side and right hand dragging this side, and the thread actually, to withstand the force that is applied by my hand, so it wanted to apply a counter force in this direction like this. So my hand is dragging this direction, and this string at this particular point is dragging this direction. At the same time, if I take at this particular hand, this hand is trying to drag in this direction, but this thread at this particular point, it wanted to apply a counter force so that it can withstand at the equilibrium stage. That means within this particular string, there are two different kinds of forces that are acting on it. These two kind of forces actually, it will be acting opposite to the applied force, that is to applied force to the string. So that means here actually, suppose if there is a string, and then from here and here, if there is a force acting like this, and if there is a force acting like this, so this is F1 and this is F2, then, usually actually it will withstand for the single force. So here actually this is the force that is acting towards this direction. It will withstand with a counter force of F1 at this particular stage. Similarly at here also, this is applied an external force of F1, and there will be a counter force that will be acting opposite direction, again F1 here. So within this particular string, at every point, there will be two different directional forces there. So one towards this direction, another towards the other direction. Got it? So when you are talking about the equilibrium at this particular stage, you will be considering this force. When you are talking about the equilibrium at this particular stage, so you will be talking about this F1. So, but ideally, internal forces are one opposite to the other. This is how actually you should be considering. Got it? Understood? So based on this understanding, try to solve this problem by applying the condition of equilibrium at this point and at this point. Can you try to solve now? Anybody got the answer? Okay, so look at here. See this. So as a general rule, right? So if there are coplanar forces that are acting, so to check the equilibrium of the forces, right? So the way we do is we will divide all the forces into horizontal component and vertical component. Now here actually there will be a tension. So here actually there is a thread. So this thread actually, so being the force is acting this direction, it has to withstand the force applied at this particular point and the support, counter support at this particular point. That means from here actually it will try to act in the opposite direction like this, and from here actually it will try to act in the opposite direction like this, being this is the tension. So this is upward and this is downward. Even here also there will be a force that is acting towards this direction. It has to withstand so that the force will be leftward. And here also there will be a force, actually this tension is applied at this particular point. So in a counter direction it will act like this. So these two forces are balancing each other so that actually this string is under stable condition. Now if you want to divide the forces, this T1 is acting upward and T2 is acting upward here, and the same T2 is acting downward here. So you can divide this into the horizontal component and vertical component. So here if you want to divide the forces into horizontal component and vertical component, you have to know the angles between the forces. So this angle is making an angle of theta. Then this component of the force which is acting upward, that is T1 cos theta. And here this angle being phi, this angle will also be phi. So this force is acting downward. So this force which is acting, the component of the force downwards, that is T2 cos phi. So T2 cos phi plus W1 is equal to T1 cos theta. So T1 cos theta is equal to T2 cos phi plus W1. This is equation number 1. So at this particular point we have applied the vertical components of the forces like this. And so exactly in the same manner there will be a horizontal component of the force because of T1, and there will be a horizontal component of the force because of T2. So T1 horizontal component of the force is here, actually this is T1 cos theta and this will be T1 sin theta. And this has to be balanced by the horizontal component of T2. So that component is, so this particular force being this is cos, so the vertical component will be, so that will be sin. So T1 sin phi, but T2 sin phi. So this is equation number 2. Similarly, if you try to identify the balance equations at this particular point, so there will be a force component already present, that is P, and it has to be balanced by this T2 horizontally. So the horizontal component of this force will be T2 sin phi. T2 sin phi, and this has to be balanced by P. And similarly T2 cos phi, which is acting upward, so this is T2 cos phi, and this has to be balanced by W2. Is equal to W2. So this is equation number 3 and this is equation number 4. So we have to be solving all these 4 equations to get the value of P, which is equal to W1 plus W2 times tan theta, and the same is equal to W2 times of tan phi. Now actually can you solve this? So it's a matter of trigonometric simplifications. Done? Okay. So from this actually you can calculate tan phi. So equation number 3 by 4 if you calculate it, So tan phi is equal to P by W2. It implies P is equal to W2 tan phi. So this is a straightaway equation. That is the second result. So from here actually, if you take tan theta, so this will be tan theta is nothing but equation number 2 by equation number 1. So tan theta is equal to T2 sin phi divided by T2 cos phi plus W1. Got it? Okay. So this one actually, so T2 sin phi. So this is equal to T1 sin theta. So this actually can replace here. So T1 sin theta is equal to P. And T2 cos phi is equal to W2. So this is W2. So W2 plus W1 is equal to T1 cos theta. So if you take the ratio tan theta equal to P by W1 plus W2, it implies P is equal to W1 plus W2 times of tan theta. Got it? Yeah. So I hope everybody got it. Take one more. A uniform circular disk of weight. A uniform circular disk of weight NW has a heavy particle of weight W, has a heavy particle of weight W attached to a point C. Attached to a point C on its rim. If the disk is suspended from a point A, if the disk is suspended from point A on its rim, B is the lowest point. On its rim, B is the lowest point. And if suspended from B, A is the lowest point. A is the lowest point. Show that the angle subtended by AB, show that the angle subtended by AB at the center of the disk is is 2 times secant inverse of 2 times n plus 1. So this is what actually he has. So here actually this is the problem statement. See this, a uniform circular disk of weight NW. That means there is a circular disk whose weight is NW. So this is a circular disc and the weight is NW. Obviously, the weight will be concentrated at the center of gravity, which is nothing but the center of the circle. So there will be a force of NW that is acting from the center of gravity of the circle. And then has a heavy particle of weight W attached to a point C on its rim. So there is a point C where the weight of W is acting downwards. So this is the weight and this point is C. When it is attached to a point A. So this is the point A. Now actually to arrive at this conclusion, see this is the center of gravity. Now if I try to identify the hook point somewhere here at the center or this side, obviously the weight has to be balanced out, right? So if I take its center at this particular location, suppose if I take A as this point, then because of this particular weight, it will try to drag down because the right side weight is more. Got it? So this can't be the lowest point. So lowest point is B. This is point B. So this can't be the lowest point because actually if I subtend at this particular one, so automatically this has to be shifted right side so that this extra mass is supported by this extra mass on the right side. Got it? So this A can't be this side. If A is on this side, the weight also will come on to this side. Got it or not? So this balance diagram you need to be drawing it first. So once it is drawn, now this is the lowest point B. See this, if the disc is suspended from point A on its rim, B is the lowest point. And if suspended from point B, so if I take the other way, so take the same circle, now actually it is suspended from point B instead of A. That means this shifted to this location. Obviously, the other one will shift to the downwards. This is point C, but this C and this C is not exactly same. Why? Because BC length is this one. Now the BC length is this one. So this location won't be changed. Got it or not? So if you look at from the bottom, so this height, if it is X, then this height can't be X. This is Y. Got it or not? I hope you understood. So because BC length, so here BC length are one and the same. That means you have to be calculating from B because initially you have taken reference B as reference to identify the point of C. So based on this understanding, now when it is hooked at this particular point, now A is the lowest point. A is the lowest point. So see this. Okay. Show that the angle subtended by AB at the center. So this is B and this is A. So this is A and this is B. Now in both the cases actually he is talking about this angle, this entire angle. So AB angle is same in both the cases. But if you look at from this side, now let us say if I call this angle as theta and this angle will be phi. So there are two different angles. Now the sum of these two angles, theta plus phi actually is the angle subtended by AB. Got it? So based on this understanding, so he asked us to find out this angle theta plus phi and it should be equal to 2 times of secant inverse of 2 times of n plus 1, where the mass of this entire disk is NW and the mass that is subtended at point C is W. So this is W and this is NW. Now try to solve this problem. So if this angle is theta and this angle will be theta and this will be phi. So in total actually what are all the forces that are present in this? How many forces are there? Total how many forces that are acting on this structure? Yeah, so there are three different forces that are acting, but the problem's statement, right, it says only two different forces, but there will be a third force which is hidden here. See this. So the weight of this particular ring, so this particular disc is NW and the mass that is attached is W, and then here actually there will be a reaction of the hook point. So this reaction, as I said earlier, it is always perpendicular to the surface. Got it? So if you draw a tangent like this, there will be a reactional force acting outward direction like this, because the mass is dragging this side and the force will be acting opposite direction. So this is a reaction. So this reaction is an unknown force. So when we are calculating the equilibrium problems, right? So this unknown force magnitude actually you don't need to know. You don't need to calculate. So if you are able to calculate, that is okay. But 99% of the cases, so for our understanding purpose of calculating this phi plus theta, is it needed to calculate the reactional force or not? It doesn't matter. So because of that reason, what we do is we will try to eliminate this force by taking the moments about this particular point. So if I take the moments about this particular point, then based on the fundamental theorem of the moments, right? So if your force is passing through the point of application of the, so from where actually you wanted to calculate the moment, then the moment will be 0. So if I take this particular force, the perpendicular distance of this force from this particular point is 0, because it is passing through that point. Then the moment is nothing but force getting multiplied by the perpendicular distance from the point. So that is anyway 0. Hence, so you don't need to consider the moment of this particular reaction force. So like that actually you will be eliminating this particular force for the calculation purpose. So if we take the moments about this particular point A in this particular case, so this is the reaction R, and then take the moments of this reaction about this particular point, all the forces. So there are three different forces, this force, and this force. If you take the moments about this force, this you don't need to consider, only two different forces are there. For that actually you need to be establishing the relation for this particular theta and phi. Based on that, exactly you do the same thing for this one, try to manipulate the equations to arrive at this. Got it? Okay, so now it is time to solve. Yeah, you can solve it now. Okay, so let me solve this. See this, here actually there is a reaction force. Now you wanted to calculate the moments about this particular point to establish the relation between NW, W, theta and phi. So for that actually you need to calculate the perpendicular distance of all the forces from this particular point. Now there are two different forces. So, and this force anyway you don't need to consider, because actually the reaction force which is passing through the point. Now if I extend like this, then this will be the perpendicular distance. So this is the force, and for this actually there will be a perpendicular distance like this. So this you need to be calculating. And then there is one more force. Now actually this force is acting downward. So this force actually for this particular point, right? So you have to be calculating. So this is the perpendicular distance. So if I say this point as A and this is B, so I call this as maybe L, M, yeah, so L, M. Now if I extend like this, I can draw a line like this, N and P I call, yeah. So here actually you tried establishing the relation between this length and this length, right? So that actually you can get a relation between these two forces, right? So here actually taking the moments about point A. So there are two forces. NW acting downwards from the center of the disc, and W acting at C downwards, right? Okay. So you note down this, I am going to erase it and then try to solve this problem. Okay. So this is how actually you can extend this diagram. Now see this. So if you take the moments about this particular point O, so one force is, so this moment, this is the perpendicular distance for the force of NW which is acting downwards. Now, and the direction of the movement is from the radius, try to draw an arrow towards the force. So this is actually the anti-clockwise direction. So anti-clockwise is NW times of the perpendicular distance. So this is AL. This is plus. And this particular moment, so that is one force is acting downwards, that is at point C. So this is point C. So at point C actually the force is acting downwards and the perpendicular distance is this one. Now if you extend this and then towards the force if you try to draw it, right? So that will be clockwise. So this is anti-clockwise direction and this is clockwise direction. So that is minus W into AM. This is equal to 0 for the equilibrium. So for the rotational equilibrium, right? So all the moments has to be vanished out. So in this particular case, this is one moment and this is one moment, this is 0 moment. So these two moments, so all the three moments together has to sum up with 0. Now in this particular case, so this can be, so this is N times of AL is equal to AM. So N times of AL is equal to AM. So AL is this length and AM is this length. Now actually if I extend that discussion to this length, so that I can take the advantage of this radius even for this one. Now this one AM, so AN can be calculated as this is equal to PC minus PQ. So PC minus PQ is nothing but this length. So this is exactly this equal to AM. So this is equal to PC minus PQ is equal to N times of AL. And also this PC is nothing but AL. Sorry, PQ is equal to AL. So this is a straight line. So 90 degrees. So this length and this length are one and the same. So if I call this AL as PC is equal to PC times PC minus PQ. Yeah, this is correct. N times of PC, sorry, this is PQ, yeah, PQ. PQ plus PQ is equal to PC. And then N plus 1 times of PQ is equal to PC. So this is one relation. So N times of PC is equal to PQ. So N times of PC is this length and PQ is this length. Now, if you want to extend this discussion, so this is radius and this is also the radius. Now, PC can be expressed as, so this angle is theta and this angle is phi. So, okay. So this angle is phi and this angle is theta. Now in terms of phi and then this length radius a, so you can express this length PC as a sin phi. A sin phi. And similarly, this length you can express as, so this is this length and this angle is theta and this angle is phi minus theta plus phi. So this angle you know, so this is the horizontal component and this is the vertical component. So vertical component will be definitely equal to this length, right? So this length will be sine of PQ is equal to AL is equal to A times of sine phi minus theta plus phi. So this is A sine theta plus phi. So if you substitute here in this particular equation, so this is going to be n plus 1 times of PQ. PQ is A times of sine theta plus phi is equal to PC is equal to A sine phi. So this A will cancel out and we have got the relation n plus 1 times of sine theta plus phi is equal to sine phi. This is the relation. Got it? So this is the first case. Initially when A is supported and B is the minimum point. So this is the B is the minimum point. In the second case, B goes here and A comes here. And phi goes here and theta comes here. That is the other case. First you note down this, we will draw the other diagram. Done? Okay. So in case 2, theta becomes phi and phi becomes theta. In case 2, A becomes B and B becomes A and theta becomes phi and phi becomes theta. So this is the case. That means exactly the same relation without making any difference. Exactly we will get the same relation. N plus 1 times of sine of phi plus theta. I have interchanged these terms. Theta plus phi became phi plus theta is equal to sine theta. So theta became phi. So phi became theta. So this is equation number 1 and this is equation number 2. From these two equations, you can manipulate and get the value of sine theta plus phi. Got it? Okay, so from these two relations, so by equating equation 1 is equal to 2 because the LHS on either sides both are same. So if LHS are same, then sine theta equal to sine phi. It implies theta is equal to phi. So both are one and the same. So that is one important conclusion. If you substitute here theta is equal to phi, then n plus 1 times of sine theta plus theta is equal to sine theta. So this is n plus 1 times of sine 2 theta is equal to sine theta. It implies n plus 1 times of 2 sine theta cos theta minus sine theta equal to 0. So I tried solving this equation. Now this is sine theta getting multiplied by 2 times of n plus 1 times of cos theta minus 1 equal to 0. So the general solutions of this is when sine theta equal to 0, then theta has to be equal to 0. So theta equal to 0, which is an impossible solution. Because if theta equal to 0, then there is no point of discussion. Got it? So both are one and the same. Now here in the second case, if you try to solve this equation, cos theta is equal to 1 by 2 times of n plus 1. 1 by 2 times of n plus 1 from this relation. So if you further simplify it, 2 times of n plus 1 is equal to secant theta. And then theta is equal to secant inverse of 2 times of n plus 1. So this is the value of theta. But actually he asked us to find out the angle between this AO and OB. So that is entire this angle, that is theta plus phi, is nothing but 2 times of theta, since theta is equal to phi. So this is going to be 2 times of secant inverse of 2 times of n plus 1. This is the answer. Got it? Understood? Okay. So you can note down this. A beam of weight W is divided by its center of gravity by its center of gravity G into two portions AZ and GB. AZ and GB, whose lengths are A and B respectively. Whose lengths are A and B respectively. The beam rests in a vertical plane on a smooth floor AC. On a smooth floor AC and against a smooth wall CB. A smooth wall CB. A string is attached to a hook. A string is attached to a hook at C and to the beam at a point D. Point D. If T be the tension of the string, and alpha and beta be the inclinations of the beam, and alpha and beta are the inclinations of the beam and string respectively, of the beam and string respectively. To the horizon, show that T equal to W times A cos alpha by A plus B times of sin alpha minus beta. So this is what actually he asked us to prove. Now see this, in the problem statement, a beam of weight W, so there is a beam whose weight is W, is divided by its center of gravity G into two portions. So AB, so AG and GB, whose lengths are A and B. So this is A and this is B respectively. The beam rests in a vertical plane on a smooth floor AC and against a smooth wall CB. So AC and CB, right? So smooth wall CB, that means this has to be C and this has to be B and then this has to be A. So this is how the beam has to be, right? So this is a smooth floor and against a smooth wall. This beam of AB is resting, and then let us say this is the center of gravity G, which is acting downwards, and this G divides this entire length into this portion A and this portion B. And there is a string actually, so that was attached to this particular beam and then tied at point C. So this is point D. So this is point D and there is a string actually that was tied from here to here. And then there will be a tension obviously dragging this side, right? So this is the tension on this particular string. This tension actually he asked us to find out. So that actually in terms of the weight W, so the weight of the beam is W, which is acting at the center of gravity. So this is W. So in terms of W, AB and alpha and beta. So this alpha and beta are the, so tension of the string, okay. If T be the tension of the string, and alpha and beta are the inclinations of the beam and string respectively. So this is the inclination of the beam and this is the inclination of the string. So alpha and beta, these are the two different angles with the ground. So this is alpha and this is beta. So in terms of this actually he asked us to find out. Now actually indirectly whether it was given or not, obviously if there is a surface contact, obviously there will be a reaction which is the normal reaction. So for this particular surface contact, so the normal reaction will be in which direction? At point A. For this particular beam, there is a surface contact here. So there will be an associated normal reaction, right? So in which direction it will come? Upwards. So that is normal to AC. And is this the only reaction or there is any other reaction that is there? Any other reaction? So at B, in which direction? It will be leftwards. So because this is the surface, so for the surface actually there will be a perpendicular force. So this is one more normal reaction S. So this I call as P. So P is upward and S is downwards and W is downwards, which is acting at the center of gravity. Now actually there are two different reactions here. So when there are two different unknowns that are coming into picture, now actually one we can eliminate by taking the moments about that particular point. The other one actually you can eliminate by solving the equations. So there is no other way. So you have to find out the value of this particular T. So there are different forces. This normal reaction, this weight and this tension. So these are the four different forces that are acting. So out of all these forces, so you have to be calculating the moments. Yeah. What exactly do you mean by beam? Beam means it's a rod, nothing more than that. So there is a rod that is actually standing inclined like this with respect to a wall like this on the base. Nothing more than that. Arun, got it? Yeah. So just a rod. So based on this understanding, try to solve this. You consider the moments about point A. So it's not a blind rule. Even you can take the moments about point B. So anything is an unknown force. So anyone you can take it. So for clarity, maybe you can take at point A. Take the moments and then try to find out the balance equations. Yeah. So here actually the tension in the string actually, so this direction. So when we are considering, right, so you are saying that actually this string actually will drag in the opposite direction also, right? So there will be a counter force if it is stretched, obviously, to withstand the force. But actually when we are considering points, right, so here actually you should not be considering as a zero force when you are taking the movements. So this was actually, this is an induced tension because of the drag that was coming from this direction. When you are taking the balance equation, you can consider the tension at this particular point. But actually, for this calculation purpose, if you consider both, right, obviously there will be no force acting on this, which is not true. So that's why actually, because this is the actual force and this is the induced force, so you can consider this particular directional force. Got it? Now, what do you mean by that? So there was a tie-up at this particular location and actually it is trying to drag in this direction. So to hold tightly like this. So actually this was a thread that was tied to this one and trying to hold at this particular point so that actually this won't slip here. Done? Noted? So does anybody got the answer for this? Now actually if you consider the movements about point A, then there are different forces. So before that actually, so there is an unknown force here. We wanted to find out the force magnitude. So for T, so this unknown force if you are able to express in terms of T, so that will be good enough because actually in the simplification you will be left with only T. So this force is acting on this direction. Obviously this tension is to balance this normal reaction. So the horizontal component of this force, this is T. So this angle is beta. So T cos beta. T cos beta is equal to S. So this is equation number 1. And if you take the moments about A, then so this force actually will not have any moment because it is passing through the point where we considered, and the other force is this force, and the perpendicular distance is, so this point and this is the perpendicular distance. So this is 90 degrees. Obviously this height is the BC is the perpendicular distance. So BC into S is equal, so this one, so this moment actually if you take it, so this is the force direction and this is the radius direction and this is the direction of the movement. So this is anti-clockwise direction. So this you can treat as plus. And then the next force is this W. W is acting downwards and the perpendicular distance is this one. So this is the perpendicular distance because this is the point of consideration and this is the direction of the force, and the perpendicular distance between the point of consideration and the force is this length. So this length being A and this angle is alpha. So A cos alpha is this length. So W getting multiplied by A cos alpha. Now the direction of this moment is this radius to force, actually if you draw an arrow, this is in the clockwise direction. Hence this you need to treat as negative. And the other force is this one, tension. So this tension actually from this particular point you need to find out the perpendicular component of the length. So this length, so this is the tension direction and this is the perpendicular direction. This length will be in terms of this BC, AC if you want to express it. So AC cos beta is the perpendicular direction, right? Yeah, AC cos beta. So AC cos beta, so this directional force. So this will be how much? Yes, sir. Yeah. So which direction it is? So AC cos beta. So this is also clockwise, minus. So this has to be equal to 0 for the equilibrium condition. Now BC into S is equal to W into A cos alpha minus AC into cos beta. Now actually these values actually have to convert into the known values. So S is equal to T cos beta. BC into T cos beta is equal to W into A into cos alpha minus AC. AC is this length. So this angle is alpha and this length cos of alpha. So AB cos alpha. W into A cos alpha. AB is nothing but A plus B cos alpha cos beta. So BC is this length. So AB sin alpha. A plus B sin alpha cos beta is equal to WA times of cos alpha minus A plus B times of cos alpha cos beta. Here actually there is some T missing. Yeah, tension. T. So there will be T here. Now actually you can simplify to bring T on one side. Yeah. So you can simplify this and tell me the answer. So here also there is one T here. Sorry, there is a mistake here. See this actually when we are considering the force of this one, right? So AC and this particular tension. So when we consider the moment of this tension, so this is the perpendicular distance. So if this angle is beta, then actually AC cos beta is this length, but we want the vertical length, AC sin beta. So this has to be sin beta. Yeah. Now you will get the correct answer. Got it? So from this actually you can simplify this. So T times of A plus B times of sin alpha cos beta cos alpha sin beta, and this is equal to W times of cos alpha. Yeah, so this has to be plus, right? So when you are taking to the other sides, yeah, so this will be negative in that case. Yeah, so this is T times of A plus B times of sin A cos B minus cos A sin B, sin A minus B equal to W cos alpha. T is equal to W cos alpha by A plus B times of sin alpha minus beta. So this is the answer expected. Got it? Yeah. So did you get a fair clarity on this kind of problems? Only thing is actually you need to identify the diagram. Yeah, WA cos alpha. You need to identify the diagram first and then actually try to identify the angles. So only procedure is to balance out the equations. One is the force equations, maybe horizontal component and vertical components, and another is take the moments coming out to be 0 for the equilibrium condition. Based on that actually you will be identifying the unknown values. So this is the final summary of this entire topic. So only these things are there. So whatever may be the number of forces, it is always resolved components along the x direction and along y direction. Each has to be separately equal to 0. That is one condition. And the moments has to come out to be 0, all the moments together. In case if at all there are unknown forces, then actually identify a point about which you take the moments so that the forces are going to be vanished out. You don't need to be considering those forces because you are considering the moments of the point where that force is passing through. So in case of unknown forces, you will be considering like that. Usually 99% of the cases is when there are some reactions. So because of the contact with the surface, so the reactions, right, so are unknown forces. Those reactions actually you will usually eliminate, so that you don't need to be considering in the unknown force list, right? So based on that, actually you will be identifying unknown forces. That's all. Got it?